which mainly focuses on the vibration analysis of the bow bridge with and without the soil foundation.
Let's come to our first part of our presentation. I'm going to give you some introduction of our motivations. The first of all is our group members aware of the significance of the earthquakes. Here I put a picture of the Takuma Narrows Bridge. This is a collapse of the Takuma Narrows Bridge, which is located in the state of Washington. It is collapsed just after 4 months after its constructions due to the aeroelastic flutter. The collapse of the Takuma Narrows Bridge provided important class in the importance of the considering aerodynamic in bridge designs. This event fundamentally changed the way engineers design bridges, especially in suspension bridge. So that's to say, in seismically active regions, the structural stability and the seismic performances of the bridge are directly related to public safety and the extent of the economic losses. Therefore, understanding and analyzing the vibration behavior of the bridge under seismic loads is critical for improving engineering design and disaster mitigation capabilities. And the second thing that inspires us is about soil structure interactions on the bridge. What does this mean? It means the mutual influence between the foundation soil. This is foundation soil and the superstructure of the bridge. The traditional bridge design often assumes a rigid foundations, but in reality, the deformation and response of the foundation soil can significantly impact the dynamic characteristics and response of the bridge. So we have to study the impacts of the soil structure interactions on the overall performances of the bridge, which is essential for more accurately accessing seismic response and enhancing design reliabilities. And in the second part, I'm going to introduce about the objectives of our project. Firstly, we are going to conduct vibration analysis using an application called ANSYS. We aim to review the influence of the foundation soil on the dynamic behavior of the bridge, helping engineers better understand and predict the performances of the bridge under actual seismic conditions. After that, we are going to use the conclusion in the answers to explore resonance effects. This goes to provide more accurate seismic response prediction models for the bridge designs, and thus improves existing design code and standards. Last but not least, we're going to achieve that we can predict the structural safety and durabilities and improve the overall performances and safety in the bridge in the seismic events.
Okay, let's continue to the background part, and let me first introduce something about the Arc Bridge. And this Arc Bridge is one of the oldest bridges in the world and has a history more than 3,000 years. And the Broad Bridge is located in the central part in New York, and its designer is covered books and unjackable wear mode. It's completed in 1862 and is classical brick styles, and is a typical example of the cast iron, and which has been a popular materials in contemporary time, distinguish itself from the traditional arc stone bridge due to its exceptional mechanic properties and its for producing. And this is attributes ensure that the bridge can withstand substanding loads while maintaining a standard and graceful appearance, such like a violins, like this, and which has been regarded as one of the most romantic places in New York. And you can see many famous films has taken this place to take like a Spider-Man and a rainy day in New York. Okay, let's continue to learn methodology.
So we constructed the 3D model of the bow bridge and conducted the vibrational analysis in ANSYS, and we mainly use this workbench. Here's an overview of the steps we took during our research project. So we simulated the 3D model in space claim, defined the material properties in engineering data, and conducted finite element modeling as well as vibration analysis in mechanical using meshing. I'll explain them in more detail in the following slides. As for the data input to prepare us for the modeling, we searched for geometric information about the bow bridge online. And it turns out that as a single span arc bridge, the bow bridge has a longer span of 18 meters, a total length of 27 meters, and the radius of arc is 1.6 meters. Well, actually, we're not able to obtain the radius arc online. So we just downloaded and printed several pictures of the bow bridge, measured the total length and the distance between the highest point of the arc and the horizontal line of the river. And then we just calculated the mean ratio and derived the radius arc. So the radius will not be as precise as it would be if we could have obtained the information directly from the internet, but it is showing our modeling. So for the materials, fortunately, the whole bridge was made up of purely cast iron, which made the whole process much easier. And the soil beneath was mainly composed of sandy loam soil. The material properties like densities, Young's modulus, and Poisson ratio were all derived from online database because it would be quite complicated if we analyze them on our own. And here are the two pictures of interfaces of the engineering data where we define the material properties. I think this is for the soil and that is for the cast iron. Depending on the geometrical properties and material properties, we would be able to build a 3D model of the bow bridge in space claim. So we actually simplified all the complex geometry characteristics, such as the gorgeous Greek-style decorations on the deck. But we did retain all the essential features, such as the single span, the long deck, and the 8 bridge supports. We also did a partition between the bottom of the bow bridge and the surface of the two soil parts in order to assign different materials to the corresponding components. When all of those were done, we would be able to analyze the finite element modeling and conduct the vibration analysis. So in both group of analysis, we chose the mesh size of 0.5 meters and the finite element shape of tetrahedron. As for the boundary conditions in the model without soil, we fixed the 8 bridge supports in 2 shorter sides of the bow bridge. As for the model with soil, we fixed the bottom and 4 surrounding sides of each soil part. We actually chose compression fixation for the 4 surrounding sides of each soil part because there's always going to be soil surrounding each soil part, and it would be quite difficult for us to really simulate all of them. The main purpose of our vibration analysis is to derive the natural frequencies and the mode shapes. As you know, natural frequencies are just frequencies at which the bridges or any other buildings will vibrate when subjected to certain external loads such as seismic disturbances, while mode shapes suggest how the bridges or other buildings will respond when vibrating at corresponding natural frequencies. So we actually conducted a total of 12 groups of different mode shapes, and that's actually 6 different mode shapes in each group. And the results will be extracted from ANSYS, which would be shown in the result part.
Yes, and this is result part, and this is the without soils vibrations, like just like single list bridge, and this 3 is up and down vibration modes, and they're in different frequencies, and they just move up and down, and okay, these 2 one are the material extension and contraction vibration mode, and you can see they move and they vibrate side to side, and the last one is the combination of 2 vibration modes, and it's both up and down and like lateral extensions. It is the vibration without soils, and this page shows the vibration with soils, and this part is the soils, and the 4 pictures is all up and down vibration modes. And the last two image shows the twisting vibration mode and different from this up and down and center content vibration modes. And you can show like this, and the last one there have lower colors, so shows it can maybe we guess that it can be more lower vibration frequencies to the without soil one. So we make we make out the line charts like this one. The first one is without soil, and the second one is with soils. And similarly, they are both like upward tendencies in order of 6 modes, but the digitals range in the first is much greater than that in the second one. You can see the first one is like A238, and but the with soil one is 2 to 5 like this. So that's because in the inclusion of both soil and 4 column storms, boundary size in soil foundation result in a large overall mass, thereby enhancing global structure stability. Moreover, this approach aligns more closely to the real life. That's why they like vibration more lower frequencies like than the without soil one. Okay, it's our conclusion points.
From the soil loss frequency, the frequency is below 20 Hz, while in the last 3 modes, it is above 25 Hz, and the overall frequency trend shows an increasing trend. For the soil impact, the frequencies of the 6 modes are far less than 10 Hz and even below 6 Hz. And for the results, we comparing the 2 groups of the results, we can find that the average vibration frequency in soil environments is much lower than that in non-soil environments, which intuitively and clearly proves the influence of soil environment on bridge vibration frequency. Here's the statement of contribution. So I am CC, and I'm responsible for modeling and preparing input data. Renly is in charge of plotting results and visualization. Alice composed introduction and objective parts in the slides, while Renly composed the backgrounds and results in the slides. I composed methodology in the slides, while Joyce composed conclusions in the slides.
Yes, and we are here and we want to special thank to our professor for your support and for your support and guidance, and also thank to our 3 TAs for your helps. And also we want to thank to you all guys for your listening, and we want to get your feedback. Thank you.
And this is the second tower to 6 the tower is 55 meters and a video. It's tilting. And next, our second experiment, the in deformation in different soil. We change the yardage of the soil. In this, our was class 1E 0 Pascal. And in this, our yardage is 1E0. In this image, our yardage of the soil E plus Pascal.
Total effect of the tower or peak, and yeah, they data of the picture, and when towers soil module a second row determining ability of the structure, and the module is fundamental features that directed the city of the and it to with the deformation or stress in the context of the soil layers, which is there having the by the YAML soil detected information behavior our built such grounds. And for and is to of the then a higher YAML indicate greater stiffness in reduce formation of the top soil layers. This increased stiffness provides additional support of the enhance its and minimum the risk of excessive deflection element. On the hand, lower YAML stiffness, the used in amplify deformation. The is compressing the structural integrity. Another is by impact the frequency deformation. And this of the picture was this inequity caused by the fact our writing playing a role in information. Firstly, person team that towers are more suspect to deform. This is because writing external. It is as nodes and forces additional can perpetuate the of bounding in the potential activities. In case of the tower, it's become hard structural changes by the angle and soft foundation or high and makes the uneven foundation and go to correct out, making the tower is or its complex.
So I'm going to why our is important in the finding these things, scientists can by understanding mental facts and with
soils. This can more complete approach in preparing kind of construct. Also, this research, this kind of soil data allow engineers to understand the stability of foundations. So they in the tower. For example, in this case, engineering are in a small soil on the north side of the foundation of the tower to use the ingredients. So the of the risk and conclude our research. This research focus on construct a simplified model, examine impact towers, the yards, the line soil layers, inclusion and vibration frequency. Through various we gathered data that we fascinating side. Initially, with that both information of and vibration frequency soil things count, but as increase height, they decrease. And so this behavior scores the relation between height and the structure more they indicate balance model which the stickiness of the soil increase information of when it's increased, and also plays a role influencing the forest vibe frequency. This suggests frequency and of the tower highly sensitive to the modulus or the source, and this result significant and provide value data on the clean the time substrates, and it can bridge between biomechanics and structural engineering and allow help preserve the historical things as the Tower of Pisa.
Okay. This says when response modeling, diagrams and the results, and PowerPoint activation on the response for background risk and the summary and key response. And this is our essay reference.
There is about needed here. You are in the preserve.
Oh.
It's really that there is considerable.
Oh. Oh.
Hello everyone, my name is Jimmy and he's Luke, and today we're gonna introduce you to our research. Our topic is impact of pore diameter on heat conduction efficiency in porous media.
Okay, first is the background. Since it is a thermal conductivity research, so let's begin with the three modes of heat transfer. The first one is conduction, and involves in a material. Heat transferred directly in a material without the material itself moving. And the next one is the convection, and involves in the movement of the fluid. And the radiation is the heat transferred by the electromagnetic wave. And in our project, it is mainly we are mainly considered the conduction. In other words, we just assume that there's no convection and radiation. We only consider the conduction. Okay, the background is that this picture is a stainless steel porous cooling plate for water purification device. Now, I don't know how exactly the purification device works, but I know that it generates a large amount of heat during working. So we need this plate to cool the device down to transfer the heat out of the system. Now, what we are interested in is that the pore size, the size of the pore on this plate affect the thermal property. These pores are set to increase the thermal conductivity of the plate, but the size of the pore also affect the thermal property. Specifically, with a small pore size, more solid phase conduction there is. And as the size of the pore increased, the gas phase conduction also increased and solid phase conduction decreased. And since the plate works as a conductor to transfer the heat out of the system, so we want the conductivity of that plate to be as high as possible. So, as mentioned before, the size of the pore affect the conductivity. So, what we want to find out is how the process affect the heat transfer efficiency of the plate. And since the small pore and large pore represents the gas phase conduction and solid phase conduction, so the problem becomes the best balance of thermal conduction between solid and gas. So so we want to find the optimal pore size that gives the plate the highest heat conductivity performance. So our objective is to investigate on the most suitable pore size for achieving good performance of heat transfer.
Okay, next I'm gonna introduce you to our methodology of solving the problem. First of all, sorry. We utilize the software ANSYS to construct the geometry model of our porous media. So we have a simplified geometry model of our media. So it looks like this. So this is a cuboid made of steel. The material of the cuboid is steel, and we dug out 4 little holes over here to simulate the pore. And then we have a fixed dimension for the cuboid, which is 1.4 meter times 0.8 meter times 0.8 meter. And then we change the diameter of the pore to see how the the data of the conduction will change. And after constructing the geometry for the media, we then determine the proper boundary conditions for the simulation process. So actually, we actually came up with a lot of ways to simulate the process. We changed a lot of, we actually tried a lot of different set of boundary conditions, but in the end, we picked the most simple one, which is one temperature, which is an essential boundary condition over this surface, and one other temperature, which temperature on this opposite surface. The temperature difference of the two surfaces are 200 Kelvin, and that will be the temperature difference, and there obviously will be a heat flux across all this surface. So the heat flux will be symmetrical over this axis. And after setting the boundary conditions, we will yield the data over here for a certain pore diameter, and then we will change the pore diameter and repeat the simulation, and then export the data to do the variable analysis. So we measure our research measure the temperature counterplot and the heat flux counterplot over this special edge. Since I mentioned that the whole model is symmetrical over one axis, we can just measure this edge and utilize the data to yield our result. So our result looks like this. So here's the data which has been processed. So this is the first one over on the left-hand side is the heat flux versus location along the path. So this different lines of different color indicates a different pore diameter. and they have corresponding graphs. So the right-hand side is the temperature versus location on the path. So so you can just take a look at all these two graphs, and next I will explain some of the features of the graph. So for the first feature is that as pore diameter increases, the fluctuation of heat flux becomes more intense, as shown in the plot, indicating a higher heat conduction efficiency. So over here, the heat, as you can see here, the yellow line over here has the highest peak and the most intense fluctuation. And this happens when the pore diameter is 0.4 meters. So it can be explained since we researched a Maxwell-Oiken model online, and this model gives us the effective thermal conductivity of mixtures. So K1 equals continuum phase and K2 is dispersed phase thermal conductivity, and we can utilize this formula to calculate the effective thermal conductivity of our geometry. So I analyzed our data and substituted in this formula and yielded that for the data range in our experiment, when the volume of the pore increases and the volume of the steel decreases, the thermal conductivity will increase, and that's why it will cause a higher heat conduction efficiency. So an alternate explanation would be that as the pore diameter is becoming larger, the edge will be thinner, as shown in this four counterplots. So the four counterplots are the heat flux counterplots. So as you can see here, this is when the diameter is equal to 0.05 meter, and in this part, you can see the heat flux is relatively uniform. So there will be few fluctuations over here. But as the diameter is becoming bigger, the edge the heat flux will fluctuate more, and resulting in all these red areas. Red areas? So as the pore diameter increases, the edge becomes thinner. So the heat transfer will take place and will concentrate on these areas, resulting in a more concentrated heat flux. And that's why the heat flux becomes more intense on the left graph, on the right, on the left, sorry. So another feature of the two graphs is that the curvature of the temperature curve increases with the pore diameter. And I think that results from the increased fluctuation of heat flux. So over here, the curvature of the temperature curve fluxes more. So it's like this, while the original curve tends to be like a straight line, So the curvature increases, and that I regarded the cause of this as the fluctuation of heat flux as well, because the heat flux Q is proportional to the first derivative of the temperature. The curvature on here, the rate of change of the slope of the temperature curve is actually the second derivative of the temperature, which is this, and we take this is proportional to the first derivative of the heat flux. So we get this, and as the heat fluctuation becomes more intense, this will increase, resulting in a more intense curvature in the temperature curve. So that's my explanation for these two features. So reviewing our research, we gained a lot of experience while constructing the model using ANSYS, because our first time doing it. It's also our first time to do a research project, so we gained a lot of experience in the process. So actually there's a lot of difficulties involved in this process, given that we have limited time and we have only 2 group members in our group. So while modeling, as I just mentioned before, we tried a lot of different boundary conditions and eventually picked the proper one for our experiment. So actually, I think the trial process is quite valuable because it provides us with experience. And also for the data analysis, after we export data, we don't know how to deal with it to yield the proper conclusion. And in the end, our TA helped us to formulate two plots as shown just now. And I think that 2 plots can be very useful for conclusion. Despite so, we still have a lot of flaws in our research. For example, we have unfixed porosity. As we change the diameter of the pore, actually the porosity changes as well. So our conclusion is only based on the condition that we have a fixed number of pores. So that's I think that's a flaw of our research. And also our data range is quite limited. We ranges from 0.05 meter to 0.4 meter. I think that's a small range. And with more time and effort, I think we can expand the data range and derive a relatively more generalized conclusion. So in the end, I want to express my gratitude to Professor Ronaldo Borja. He gave us a lot of advice on the modeling part and data analysis part. And I also want to thank our TAs, especially Mr. Liu, who offered us a lot of help while doing while making the PowerPoint and analyzing the data. And that's our end of the presentation. Thank you.